Oh, hello. I'm sorry for some technical problems. Uh, is there enough participants? Now you can come, yes? Okay, let us wait a bit of time. Maybe somebody join us. Okay, let's begin. And we have I'm sorry. Where is it? I'll just try to open our problems. Okay, I'm sorry. Now I'm ready, and let us start with the first problem. Find all natural numbers among 1, 2, and so on, 10, such that there is a field with n elements. Okay, this is the link to our board. Sorry. Okay, and what do you know about order of finite fields? Was there something about this order when we have F is a field, then the number of elements in F may be equal to what numbers? Do you know it? I'm sorry, since I had some technical problems, can you hear?
Yes, we can hear, but like this, the question is strange.
This there was nothing about this, yes?
I don't remember.
Okay. It's strange because this is the first task, and I hoped that there was some theory about it. Okay, let us maybe remind, maybe just find it. Okay, theorem. Theorem is that if F is a field and F has a finite number of elements, then this number is a prime number in some power. There wasn't such theorem. The proof is not very elementary. Let me give a sketch of this proof. The proof is that if we have F and the characteristic of F equals to P, then there is a subfield in F which is isomorphic to ZP. And this F is a vector space. Over this subfield, and this implies that F, if dimension of this vector space equals to alpha, then the number of elements in F equals to P in power r. This is just the sketch. I don't want to give the whole proof. Was something like this in your lecture course? There wasn't, yes? Okay, then now we have this theorem, and the problem is rather simple because we just need to find all the numbers of which are powers of prime numbers among this set 1, 2, 3, so on, 10. Of course, every prime number is the power of prime, and there are two elements, 4 and 9, which are not prime. So among these numbers, there are fields with 2 elements, 3 elements, 4 elements, 5, 9, oh, sorry, 7, 7 and 9. This is the answer. There is no fields. There are no fields with orders, for example, 6. Oh, I'm sorry. I'm very sorry, because 8 is the power of 2. Yes. So we have the field of with 8 elements and with 9 elements.
Excuse me, and what about 1?
1, it's a philosophical question, because it's we want to it seems that the definition of field says that 1 which belongs to this field does not equal to 0 which belongs to this field. but it is we can take different definitions and the field with one element uh, exists in some of definitions and does not exist in another definition. Let us think that there is no field with one element. It's more convenient. It seems that there is such axiom that 1 is not equal to 0. Okay, number 1 is off. Okay, it is clear. It's very simple. If it's very simple, if we use this theorem, of course. Okay, let's begin with number 2. We have a field of characteristic P, and we want to show that this mapping is a homomorphism. Okay, let me remind what is characteristic. If I have a field, I have 1 in this field. This is natural element with respect to multiplication. And I can add 1 to itself. In some fields, I can obtain 0 by adding some elements. If I add p elements and p is the minimal number such that I obtain 0 adding p once, then p is characteristic of f, and it denotes by char f. It's for some fields you can't obtain 0 by adding some ones. Then characteristic of f is called 0. If there is no such p, then characteristic of f, it's more convenient to say that it's infinite, but the definition that it is 0. There are some arguments, but they are rather difficult. We don't know. We don't need these arguments. Just we say that characteristic of f equals to 0. For example, if I have the field ZP, then of course the characteristic of this field equals to P. And if I have, for example, the field of real numbers, then its characteristic equals to 0, because in real numbers we can't add some ones and obtain 0. It's easy to see that characteristic either 0 or a prime number. Okay, and now we have a field f with characteristic p, and we consider the following mapping: x maps to x in power p. We need to say that we need to prove that this is injective and this is homomorphism. Please say me what is the definition of homomorphism? This is phi. And what shall I check? What shall I check to say that phi is homomorphism? It's rather simple question.
Excuse me, and what is F? Is it a ring?
F is a field. Today we work with fields. There is no definition of characteristic in case of arbitrary ring, just in case of fields. What is homomorphism? Yes, but the homomorphism of fields, this is the homomorphism of rings. It should be homomorphism from F to F. What just means the word homomorphism? The word homomorphism means that all operations maps to operations. So phi from x plus y equals to phi from x plus phi from y. And phi from x multiplied by y goes to equals to phi from x multiplied by phi from y. This is just.
Excuse me. And what about phi from 1 equals to 1?
Yes, let us say it, but this first two implies the third. It can be shown that this is this for I'm sorry, no, this is there is no such axiom phi from 0 equals to 0, and this is follows from the first. But phi from 1 is 1. It is not correct because there is a homomorphism. All the ring, all the field goes to 0, and it's just correct homomorphism. So with 0, there is such, and this follows from the first. And for 1, there is no such rule that phi from 1 equals to 1. Okay? So it can be showed that this implies this. So I need not this row. Okay, let me just check these two. The second is very simple. The second says that x, phi from x multiplied by y equals to x, y in power p. This equals to x in power p multiplied by y in power p. Here I use the commutativity of multiplication, but in field we know that field is a commutative ring. And so this is phi from x multiplied by phi from y. Okay, we have checked the second law, and we have not used that P is characteristic of F. This is correct for every part, P. And the first is rather strange. For example, when characteristic equals to 2, then we have from first, we have the following rule that x plus y square equals to x square plus y square. But from the school, you know that you're very strange student if you think that this is correct, because every student know that there is additional term plus 2xy. But in characteristic 2, we have that 1 plus 1 equals to 0. So 2 equals to 0. And so this is just 0. And this equation is correct. For example, in Z2, this equation is correct. Okay, and what about common case? Characteristic is equal to P. Then x plus y in power P, which is phi from x plus y. We have, we need some calculation about x plus 1 in power P. Do you know the formula of binom? That this is the sum from e equals to 0 to pi, binomial coefficient, n, oh, I'm sorry, pi I, and this is x in power I, y in power pi minus I. Do you know such formula?
No.
Do you know what is the binomial coefficients?
No.
Maybe more convenient in Russian definition, this is C in I. There was not such formula. Okay, let me remind. For some people, this is new. Just a simple formula, rather simple, but not very simple. Okay, we have such definition. This is number which we call n factorial divided by k factorial multiplied by n minus k factorial. This is the number of possibilities how to choose from n elements some k elements. For example, if you have, I don't know, 7 balls, and you want to choose 5 of them, then you can do it by 7 factorial divided by 5 factorial divided by 2 factorial. This is 7 multiplied by 6 divided by 2. This is equal to 21. So you have 21 possibilities to take 5 elements from 7 elements. And there is a formula of I don't know how it correct in English. In Russian, it's binom Newtona. In English, maybe Newton's binom. And this is the formula that x plus y in power n equals to this sum. Sum from I equals to 0 to n. This n I, x in power n, y in power, I'm sorry, x in power I, y in power n minus y, I. The proof is rather simple. You just open these brackets, so just multiply and think that you can choose either x from every bracket or I or y. And the number of cases when you take I axis is this number. For example, for n equals to 2, I should remind that 0 factorial equals to 1. For n equals to 2, you have x plus y in power 2. It is equal to, I'm sorry, in power 2. It is equal to binomial coefficients of 2 and 0 multiplied by x in 0, so y squared, plus binomial coefficient from 2 to 1 multiplied by x, y, and binomial coefficient 2 to x squared. It's rather easy to check that this equals to 1, this equals to 2, and this equals to 1. So it is just the formula of x plus, I'm sorry. Get a link to this board. Okay. There is some, I need to get you. And this is the link. There's my chat. Sorry, I have a chat when I show the board. So this is the link. Okay, and now we try to use this formula to our situation. We have a field of characteristic P, and we have this formula, x plus y in power P equals to this guy. But this guy, let me remind that this is This is just p factorial divided by I factorial divided by p minus I factorial. And it is divisible by p in all cases when I does not equal to 0 or to pi. So this equals to all these elements except the first and the last is divisible by p. And in our field, since characteristic equals to p, then p equals to 0. So in this sum does not equal to 0, just the first element and the last. So, and p from the binomial coefficients p0 and pp equals to 1. So this equals to x in power p plus y in power p. And this shows us that the first law is correct, and phi is a homomorphism. So we have checked that phi is a homomorphism. Now we should check that phi is injective. Do you know how to check that some homomorphism is injective?
Well, if its image is equal to 0, then it's injective.
No, not image, but the kernel. But you're correct. If the kernel phi is injective, if and only if its kernel equals to 0. Yes. So the kernel is a pre-image of 0. So we need to check for which x we have x phi from x, which is equals to x in power p, is equal to 0. But in field you have no zero divisors, and so you have no some nilpotents. So if x in power pi equals to 0, then x equals to 0. So the kernel of this phi equals to just 0. Nothing more. And this implies that phi is injective. So by this theorem. Okay, we obtained that phi is a injective homomorphism. And now the last part of our task says that, says that if f is finite, then phi is isomorphism. It's rather simple because we know that phi from f to f is injection. If we have two sets with the same number of elements, and you have an injection from one set to another, then this is a bijection since the numbers of these sets, the orders of these sets equals. So if f has finite number of elements, I'm sorry. Uh, if the number of elements in F is finite, then every injection between F and F is bijection. So this is bijection. And by definition, isomorphism is just a homomorphism which is bijection. So, of course, in the case of finite field, every injective homomorphism is isomorphism. Okay, let's proceed with number 3. We need to produce explicitly the field of with 4 elements. It seems that this is a very, very useful task. So let us try to do it. Do you know how to produce explicitly this field in this field which has pi in the power k elements? It produces by the following construction. We have z pi. We consider the field of all polynomials with coefficients in z pi. And we consider the factoring of this field of polynomials by some irreducible polynomial by the ideal which corresponds to which is generated by some irreducible polynomial. F is irreducible, and the degree of f equals to k. This is just the common construction of finite fields. Did you have such a construction in your lecture course? Or you don't remember? Okay, I understand that this look very, very difficult, but let us give an example, and maybe after this example you change your mind and you say that this is not so difficult. I hope so. Okay, we need the field F4 which has 4 elements. So 4 equals to 2 in power 2. We need that pi is prime number, so 2 is prime number, and 4 is a power of prime number. Okay. Then, by this construction, we need to take z2. We need to take all the polynomials with coefficients in z2. We need some irreducible polynomial of degree 2 in this ring. Okay, let us it seems that we have find such a polynomial on the previous seminar, but let us do it. To find an irreducible f, we want all the polynomials with degree 2. There are 4 of them. X squared plus 1, x squared plus x, and x squared plus x plus 1. Since all the coefficients are either 0 or 1, then we have not some possibilities except these 4. This is not irreducible because it has the root 0. This is not irreducible because 1 is the root of this polynomial. This is not irreducible because either 0 and 1 are roots of this polynomial. And this is irreducible because 0 is not root and 1 is not root of this polynomial. So we can take f equals to x squared plus x plus 1. Okay, and then f4 isomorphic to z2, all polynomials over z2, and factoring by this ideal, which is generated by x squared plus x plus 1. Okay, this is this construction, but what are the elements? We need 4 elements in this field. What are these elements? These elements are just classes polynomial g plus this ideal. But we can change this g. This is f. If we have, if we add to this g some polynomial which is divisible by f, for example, f multiplied by h, and plus this ideal, then this class equals to this class, because this f multiplied by h belongs to the ideal. So what is the simplest polynomial which belongs to this class? We have some g, and we want to correspond all the polynomials of such way, of such view. And the shortest polynomial in this class is just the remainder of g divided by f. So it equals to r from x plus this ideal, and this r, degree of this r, less than degree of f, which is equal to 2. So r is an linear polynomial. And so let me go to the next frame. I remind that f4 corresponds to z2 from x and factoring x squared plus x plus 1. And here we have classes g plus ideal given by f, and this g we can choose such g that degree of this g not bigger than 1. So we have such polynomials of G. 1, 0, x, and x plus 1. This is all possibilities for G. I'm sorry, I had R. Okay, let us use G. It's all. Okay, and this is 4 elements of our field. If we should be more formal, then this is not such elements, but this is classes 1 plus f. This is 0 plus f. This is x plus f. And this is x plus 1 plus f. And it is very important to understand this construction. So please ask questions. Is it clear how to obtain the field of the field with 4 elements? It is clear that this is these 4 elements. Please say something. Is it clear or it is not clear? All is good or all is awful? Do you have some comments? Unfortunately, you have not some comments. Okay, I don't know. Let me try to multiply. Our task is to compute the product of 2 arbitrary elements. So we have 4 elements. Now let us compute the product of 2 elements. For example, I want to compute product x by x plus 1. How to deal with it? I just compute this product. It is x squared plus x, but it should be one of these 4 elements. How to get this for these 4 elements? Let me remind from the previous frame that the class of G is equal to the class of G plus FH, and the simplest element is the remainder of division G by F. So now I have, this is G, this is F, and I should find the remainder of x squared plus x divided by x squared plus x plus 1. Of course, in Z2, remainder is equals to 1 because this equals to this plus 1. So we have that x multiplied by x plus 1 equals to x squared plus x, but it is equal to 1. If you want to add elements, then, for example, x plus 1 we have we add it in common case 2x plus 1, but in Z2 2 equals to 0, so this equals to 1. Let me give another example. For example, I want to multiply x plus 1 by x plus 1. It equals to x squared plus 2x, but 2x equals to 0, x squared plus 1. And x squared plus 1, what is the remainder of x squared plus 1 when we divide it by f? Just x in Z2, so it equals to x. If I add f to this x squared plus 1, I have 2x squared, which equals to 0, plus x plus 2, which equals to 0. So this is x. Okay, is it clear how to add elements in this field and how to multiply elements in this field? It's very difficult when you keep silent. Please, you can write something in chat or you can say me if you didn't catch something. Okay. Let's proceed. Now we want to use this construction in another cases. So now we have Z8 or F8, and we want to deal with it. First of all, we need to understand that x in power third plus x squared plus 1 is an irreducible element. Okay, let us check. We have Z2 from x, and there are two polynomials. First of all, x in the power third plus x squared plus 1, and the second is x in power third plus x squared plus x, I'm sorry, plus 1. And we need to check that both of them are irreducible. Okay, we know from the previous seminar that a polynomial is irreducible if the polynomial of degree not bigger than 3 is irreducible if and only if it has no roots. So let us check if these polynomials has roots. We have only two possibilities for root, 0 and 1. We substitute 0 to these polynomials and we obtain 1. And we substitute 1 to these polynomials and we obtain also 1. So neither 0 nor 1 are roots of this polynomial. So these two polynomials are irreducible. Point B, show that the map by this rule is not a homomorphism. Okay, we have two construction. The first, this one, and this one. Oh, I'm sorry. Here is z, because we want to differ these polynomials. No, not z by but y. Uh, here is y, so on. And we want to consider ax squared plus bx plus c. What is the elements of this field? The elements of this field has the following view: ax squared plus bx plus c. Why? Because we need to find reminders when we divide by x in the third plus x squared plus 1. The degree of this polynomial is 3, so the degree of reminders is not bigger than 2. So all the reminders has such view. All the reminders, all the elements in this field, and all the elements of this field has the following view: a x in the third I'm sorry, or a y squared plus b y plus c. So there are 8 elements because there are 2 possibilities to A, 2 possibilities to B, and 2 possibilities to C, and so on in the right. But if we correspond this mapping, this is not a homomorphism. Let us check it. For example, I want to check that x multiplied by x in x squared. What is it? X multiplied by x squared. We have already understand what is the multiplication in such construction. This is equal to x in the third, but x in the third equals to what? Can you say me what is x in the third power in the left part? What is the remainder of x squared in the third with when we divide it by x squared plus x in the third plus x squared plus 1? Please say me. This is a very simple question. If I divide x squared by x squared plus x squared, I'm sorry, if I divide x in the power 3 by this polynomial in this ring, what is the remainder?
X squared plus 1.
Of course, the remainder is x squared plus 1. And we shall say that x in the third equals to x squared plus 1. And here, this is if I say that y multiplied by y squared, then I obtained y in the third by here I divided by this polynomial, and I obtain the remainder y plus 1. So if I try to say that this phi is homomorphism, then it should map x to y, x squared to y squared, but the product of x and x squared equals to x squared plus 1, and by this phi it goes not in y plus 1 but in y squared plus 1. So phi is not a homomorphism, and this is not isomorphism. But from lecture course, we know that there is just one field with 9 elements, which is isomorphic to this one and which is isomorphic to this one. So there is isomorphism between these two fields, but this is not field. This is not phi. This isomorphism is more complicated than this just phi, which goes x to y and squared to y squared. This is not homomorphic. Okay, maybe what is the most interesting here? Okay, let us do the point C in number 4. Okay, no. Let us deal with the fifth task, and I want to give some solution of the fifth. We have the field with 8 elements here, F8, which is constructed as Z2 from X and factoring by X squared plus X plus 1. X in the third plus X plus 1. Okay, and we have a polynomial H, which is 1 plus X squared. And the polynomial G, which is X. And we want to compute the coefficients of H, Hg, Hg square, and Hg cube. H, Hg, Hg squared, and Hg cubed. Okay, we need to compute the polynomial of H because we know that H equals to 1 plus X squared. So now let us to compute coefficients of Hg. What is Hg? hg is x square, x in the third plus x. And now we compute the remainder by when we divide by x cubed plus x plus 1, and this remainder equals to 1. Okay, what is hg squared? Hg squared, because of course it is hg multiplied by g. This is 1, and this is g. This is just x. Now we want to multiply h by g cubed. This equals to hg multiplied by g squared, and this is equal to x squared. So that's all. We find all these guys. And now we need to compute the matrix A of the linear map psi in the basis. And what is psi? I didn't catch. It seems rather strange because there is no psi here. Okay, let us deal with I don't know what is the fifth psi. Let us deal with number 6, maybe. It seems that in the fifth, it seems that okay. Let me define. I'm sorry. Let me define the psi by this rule. F, maybe G, goes to some polynomial S goes to S multiplied by G. This is equals to S multiplied by X. Here is G is equals to X, and so we want to obtain this matrix. Let us say what is this psi. Psi from 1 equals to X. Psi from X equals to X squared. And the psi from X squared equals to X in the third power, but X in the third power in our field equals to X plus 1. So we obtained this psi. This is the definition of psi. I'm sorry. There is no such definition in your sheet, in your list with tasks, but it's just abused. So we need the matrix of this psi in basis 1 x x squared. Okay, let us produce it. 1 goes to x, so the first basis vector goes to the second. So the first column is 0, 1, 0. The second basis vector goes to the third. So this is 0, 0, 1. And the third vector, basis vector, goes to the sum of the first and the second. So the third column equals to 1, 1, 0. So this is the matrix of linear mapping psi, which is defined by S goes to Sx. And now, if I want to obtain G multiplied by H multiplied by G in 6, I know that H corresponds to the vector, what is H? I'm sorry. H is x squared plus 1. So H is such vector. And if I want to compute H multiplied by G in the 6, it is psi from psi 1, 2, 3, 4, 5, 6 from G from H, and this is A multiplied by A multiplied by A, and so on. Let me say that A in the 6th power multiplied by this vector. Okay, and to compute G multiplied by H multiplied by G in the 6th power, I need to compute A in the 6th power multiplied by this vector. Okay, and what is the reason? I say that if I multiply this matrix by this vector, I obtained just 1, 0, because 2 equals to 0, 0. Then, so I have this deal 1, 0, 1 goes to 1, 0, 0. This 1, 0, 0 goes to what? When I multiply this matrix to 1, 0, 0, I have the first element of my my matrix, so it goes to 1, 0, 1. It goes to 0, 0, 1. It goes to 1, 1, 0. This is 1, 2, 3, 4. And then I need to compute this matrix A multiplied by 1, 1, 0. It is just 0, 1, 1. And the last, I need to compute A multiplied by 0, 1, 1. And it is equal to 1, 1, 1. So this corresponds to 1, 1, 1. and this is 1 plus x squared. This is the answer when we compute g multiplied by h multiplied by g6 in the 6. So we have solved the number 5. I'm sorry, just, so in the 6, you can just compute. Let me give an idea. You have F16, and you have F16 with star. This is the group of all non-zero elements with multiplication, and it corresponds to this is isomorphic to Z15. And the first point of number 6, that an element G is a generator when G in the 5th does not equal to 0 and G in the 3rd does not equal to 0. This is because we understand that the order of G in this group is divisible by is a divisor of 15. So this order can be either 1 or 5 or 3 or 15. And if G in power 5 is not equal to 1 and G in power 3 is not equal to 1, then order of G is not equal to 5, is not equal to 3, and it is not equal to 1, because if it is equal to 1, then G in, for example, 5 equal to 1. Then, of course, G has order 15. То есть, the order of G equals to 15. So we have solved number 6, 5, and in 6b you want to show that X is a generator of Z 16 with star. So you just need take X here, and you just need to compute X in the 3rd and X in the 5th. If it is not equal to 1, then you have proved that X is the generator. So it seems that that is all. Thank you very much for this extra seminar.
Thank you. Goodbye.
Thank
Yep,
you.
thanks.